In this video, I want to talk a little bit about optimal transport problem, which is a useful concept to have in your toolbox when dealing with a lot of deep learning problems. In a nutshell, this problem has to do with producers and consumers on this type of like a bipartite graph. For example, you can assume that A and B are like, let's say, two units that, let's say, provide certain resource. For example, it could be a mine that provide a certain material, and X, Y, and Z are factories that need that material. This example kind of showcases this type of kind of supply and demand problem. Let's assume that A and B both can like supply to all X, Y, and Z. Let's also assume that there's going to be a cost associated with the transportation of the material from, let's say, A to X and B to X, and this cost is not necessarily the same between A and B to X, but we still are going to assume certain consistencies that we'll talk about. One assumption is the consistent cost of transporting, let's say, one unit from a provider I to a consumer J. For example, if you have 2 units, it'll be 2 times that cost, 3 units, 3 times that cost. So in that sense, it is linear. With that type of assumption, and for example, you can have a cost for transporting 1 unit of resource from A to X. Let's say it be C1, let's say it could be like a number like 3, and let's say you have another number for which is not necessarily the same as before, for transporting 1 unit of resource, let's say from B to X, and therefore you kind of have like this transportation plan. So the transportation cost is going to be basically the PIJ, or the plan of your transportation from provider I to resource J, times the cost associated with I and J. So Ci and J, we assume that that matrix is going to be something that has to do with the transportation costs from provider I to resource J. So there's that. Note that given that the Cij's are costs, we assume that they are all non-negative. So, you have that. And the overall matrix P, which is of dimensions, it has the number of rows the same as the number of providers, the number of columns the same as the number of consumers. This matrix P is going to be called a transportation plan. As you can probably imagine, the problem of optimal transport has to do with trying to kind of provide these resources in a way that you spend the least amount of cost. Therefore, looking back at the cost again, D is the overall cost that you're paying, and you kind of want to allocate these transportations in a way that this overall cost is minimized. Note that you also have constraints in this optimization problem. One constraint is that PIJs are over 0, and for each one of the rows of the transportation plan P, if you sum it all up, you're going to end up with Ri, which is basically Ri, and then the same thing for going over each one of the columns and sum it all up over the columns. So Ri is basically the amount of resource that the provider I provides, and Cj is the amount of resource that the consumer J consumes. You can normalize this type of supply and demand in a way that if you go over all of the providers, all of the amount of the resources that they provide summed together will be amounted to 1. And you can do the same with the consumer side of it, and you will get to 1. You can assume that in this case, we're assuming that kind of the supply and demand are matched, in the sense that if you have like 100 supplies provided, you have 100 supplies consumed. But again, so this is not important for this problem. In this case, just note that when you do the normalization, you have like 2 probability distribution like things, R and C, which are 2 vectors that basically are going to have like a summation of 1. Now with that knowledge, you can see that this distance D is going to be kind of a distance between the distribution R and C, kind of like a check of compatibility between R and C. Now, it is plausible to assume that there are certain choices for C in which, when you look at the cost for I and J, if it is 0, it means I equal to J for, let's say, the matrix, Cij. And then Cij plus Cjk is kind of satisfying the triangle inequality, therefore resulting in a metric distance. Now, the optimal transport problem is a convex problem, as you can see on the left. Now, we can go towards the modification of this problem and define the sinkhorn distance. Now, consider the same distance over there, but instead of having the assumption of Pij's being over 0, instead you're going to look at the matrix, the transportation plan P, and you're also going to look at this matrix, which is a result of R times C transpose, which is going to have the same dimensions as P, and you want to limit and put an upper bound on the KL divergence between these two. Now, you can look at basically the sinkhorn distance, and let's discuss this problem a little bit in more detail. First off, let's compute the KL divergence between P and R C transposed. It's going to obviously be, so let's follow the KL divergence formula. You're going to have this probability versus this probability value. Let's expand it. You will have this type of formulation. Now what happened here is that first of all you kind of extracted this component, so you have Pij log Pij, which is going to be the negation of the entropy of P, and then on these sides you have basically this formulations. Now when you look at the Ij, Pij summations over here, based on the assumptions, you know that this is going to be equal to this, because if you sum over j's you're going to end up with ri's, and you're going to have the I remaining in this one, and the same goes with this one. So you can have basically the entropy of R and entropy of C, assuming the C and R are both kind of like, pseudo distributions. Therefore, when you go back to the assumption of the KL divergence being upper bounded by the parameter alpha, you're basically encouraging this, which means that because the sign behind the P is negative, you're kind of encouraging the entropy of P to be be larger. Now, you can reformulate this problem and put this entropy as this condition in the objective, and thus helping kind of resolving the issues with the constraint. Now you can use the Lagrange multipliers and put everything in the objective like this. And now in order to kind of deal with this, you want to find the point in which there is an extremum. So you want to take the derivative of this with respect to Pij's, or in general with respect to P, and find out where it becomes 0. Going over this, you're going to set this like this to 0, and therefore you're going to have, so looking at this, you're driving it with respect to Pij. There's going to be one Pij with the specific I and j over here, so you will take its coefficient, which is Cij. On the side of entropy, you have basically Pij log Pij, which if you derive it with respect to Pij, it'll be log Pij plus Pij times 1 divided by Pij, which is 1, and you have this. And then on these sides, it's kind of clear. So for the Pij that you have specific in mind, you have one mi multiplied and one nj multiplied, so you have these two as well, equal to 0, and now you can use this to compute the Pij. Therefore, Pij becomes this exponent, and this exponent, which you can formulate. Okay, so you can take this one, call it ui, take this one, call it vj, and then everything is kind of dependent on this cost function over here. And one thing to just generally note is that if you take this negation sign and the Cij, so if you take lambda times minus Cij, you're kind of looking at a consistency measure instead of a measure of dissimilarity. Note that Cij, as denoted here, are costs, so yeah. So if you vectorize it, you will have P equal the diagonal version of what U, the diagonal matrix version of V, and times x of minus lambda cc being the matrix. Now this, and optimizing this, was accidentally studied in a paper, and basically we know that this is going to have like a unique solution by a coefficient, meaning that you don't need to worry about like other solutions existing, and then therefore this problem can be generally easily solved, or at least by a in a computationally efficient manner. So now that we talked about optimal transport, an example of this, kind of a famous example of this, is a paper called SWAV. I think the paper title is Unsupervised Learning of Feature Representations or something. It's a famous unsupervised work by Meta. Generally, the idea here was that they defined a lot of prototypes. I'm not going to go through the details of the paper, but the idea is something like this. So you have k prototypes, for example, 1,000 vectors of 128 dimensions. And you represent multiple views of one image into vectors that are of the same dimension, and you kind of compare them against each other. Looking at the transportation polytope, they kind of make these assumptions, meaning that if you have a Q, which is kind of similar to a P, what you have is that if you sum every row of it, you're going to end up with 1 divided by k, and if you sum every column of it, you're going to end up with 1 divided by b, and this is defining the transportation polytope. When we had previously the minus lambda c, they basically defined the minus c of that previous equation as this. And basically, if you look back and define c as we did, the measure of kind of like that, one thing you have here is that what they say is that, okay, let's say you have prototypes and you have the representations of the images. You can use the dot product between them in order to kind of have a measure of similarity, and you can put this negative sign to have like a measure of dissimilarity. So if you put this formulation in the previous assumption minus lambda c, you will get lambda ctc. And then they use this, they have multiple sinkhorn iterations, and the idea is to generally use the result of the optimal transport as a guide and assign the prototypes to individuals. And now, if you have one image and you have multiple representations of that image being assigned to these prototypes, you will have a code for each one of these different views. And the idea is that they want to have the code assigned to another view of the same image match the probability distribution generated by the model for that specific image. And that is what they kind of do. So I haven't gone through the paper a lot in this video, but like the overall idea is that, and they use the optimal transport in this space. So optimal transport is a very useful concept to know about.